How do extensive property ratios become intensive properties? Imagine you have a big jar of sugar and a small jar of sugar. If you measure the amount of sugar in each jar, the larger jar obviously has more. That's because the amount of sugar depends on how much you have. These are called extensive properties because they change when you change the size of the system. Now, think about the temperature of the sugar. No matter how much sugar you have, the temperature stays the same unless you heat or cool it. That's an example of an intensive property, because it doesn't depend on how much sugar there is. In thermodynamics, extensive properties include things like mass, volume, internal energy, and enthalpy. When you double the amount of material, these properties also double. But if you take a ratio of to extensive properties that grow proportionally, something interesting happens. The size dependence cancels out, and the result is an intensive property. Let's look at density, which is a common example. Density is the ratio of mass to volume. Both mass and volume are extensive properties. If you double the amount of material, both mass and volume double. When you divide mass by volume, the doubling cancels out, so the density stays the same. That's why density is an intensive property. Other examples include specific volume, which is volume divided by mass. Since both are extensive, dividing them makes a property that doesn't change with the amount of material. The same goes for specific internal energy and specific enthalpy. These are internal energy and enthalpy divided by mass, making them independent of how much material you have. So, the key idea is that ratios of extensive properties that grow together with the system size end up being independent of size. This is because the proportional growth cancels out, leaving a property that describes the material itself, no matter how much you have. This concept makes it easier to compare different systems or states because these properties stay the same even if the system gets bigger or smaller. Understanding this helps us analyze and describe thermodynamic systems more clearly and accurately.